Okay, so on the second part of the lecture about mathematical induction, now we will solve problems involving fractions that have similar denominators. And I'm also going to answer a problem wherein there are dissimilar just to recall what we did on the first part. So first would be answering a problem that has dissimilar fractions as you can see here. So again, the first step is to verify. So we are going to verify for n is equal to 1, 2, and 3. Again, on the right side of our equation would be n plus 1, n plus 2 over 3. And on the right side would be the first number or term of the sequence on the left. So 1 times 2 it would be equivalent to 2. And we're just going to substitute 1 to all the n's. So that would be 1, 1 plus 1, and 1 plus 2 over 3. So 2 is equivalent to 1 times 2 times 3 over 3, and we can cancel out 3. So 2 is equivalent to 2. So as you can see, for n is equal to 1, the mathematical statement would still be valid. So continuing on for n is equal to 2, again on the right side, that would still be our equation, n times 1, n plus 1, n plus 2 over 3. And on the left side, we're now going to use the first two terms of the sequence. So 1 times 2 is 2, plus 2 times 3 is 6, is equivalent to, again, substituting all the n's to 2. So 2, 2 plus 1, 2 plus 2 over 3. So 2 plus 6 is 8, right? And then on the right side, that would be 2 multiplied to 3 multiplied to 4 over 3. Again, we can cancel out the 3. So that would be 8. 2 times 4. Again, 2 times 4 is also equivalent to 8. So for the last verification, for n is equal to 3, again, on the right side, that would be n plus 1, n plus 2 over 3. On the right side, we're going to use 1 times 2, plus 2 times 3, plus 3 times 4, or the first three numbers of your sequence. So 1 times 2 is 2. 2 plus 2 times 3 would be 6. 3 times 4 would be 12. All right, so this is 2 plus 6 plus 12 would be 20. Again, substituting our n to 3, so that would be 3, 3 plus 1, 3 plus 2 over 3. And we can already cancel this out. So 3 plus 1 would be equivalent to 4, 3 plus 2 would be equivalent to 5. So for step number 1, as you can see, for n is equal to 1, n is equal to 2, and n is equal to 3, our mathematical statement is valid. So we can already go to the induction hypothesis. Again, this is the easiest because all we need to do here is to substitute all the n's to k's. So this would become 1 times 2 plus 2 times 3, 3 times 4 plus k, k plus 1 is equivalent to k, k plus 1, k plus 2 over 3. All right. So again, no, again, this should now become our equation 1. So for the proof of induction, we will have our n is equal to k plus 1. All right. So from our induction hypothesis, 1 times 2 plus 2 times 3, we will now determine the k plus 1 term. All right. So the k plus 1 term would come from, would come from your star. Again, what is our star? Going back to our original equation, our star is this one. All right. Okay. So we're going to substitute k plus 1 to our star. So that would become k plus 1, k plus 1 plus 1. Or simplifying, that would be k plus 1, k plus 2. And this would be added here. All right, so that would be k plus 1, k plus 2, and k plus 1, k plus 2. And to prove that, we're going to have our equation 1 and equation 2. So again, this would now become our equation 2. So for our equation 1, what's written there was n plus 1, n plus 2 over 3. And for our equation number 2, that would be k plus 1, k plus 2 over 3 plus k plus 1, k plus 2. So here we will substitute n to be k plus 1, and on equation 2 we added the k plus 1 term. So if we substitute our n to k plus 1, that would now become k plus 1, k plus 1 plus 1, k plus 1 plus 2 over 3. So simplifying, that would be k plus 1, k plus 2, k plus 3 over 3. All right, so again, on the right side, this is also a fraction. So our LCD now would become 3. Again, you do this process, LCD, so 3 divided by 3, right? 3 divided by 3 is 1, multiply to the numerator. So that would be k plus 1, k plus 2, plus 3 divided by 1, multiply to the numerator. So 3 divided by 1 is 3, multiply to the numerator would be 3, k plus 1, k plus 2. So again, if you're going to observe the numerator, there are similar terms. Again, there are similar terms. So what are the similar terms? The similar terms are k plus 1 and k plus 2. So if I'm going to remove this k plus 1 and k plus 2, the remaining term on the first would be k plus. Again, if I remove k plus 1, k plus 2, so the remaining term is 3. So as you can see, the left is already equivalent or equal to the right. So I can already go to the conclusion. Again, we're just going to state the obvious, which is similar to what I've written before. So the mathematical statement is valid for n is equal to 1, n is equal to 2, n is equal to 3, n is equal to k, and n is equal to k plus 1. So again, as I have mentioned on this number that you have seen, We used LCD, and the denominators of the two fractions that we encountered, they have dissimilar terms or dissimilar denominators. Now, on the next problem for this one, we are now going to be dealing with similar terms, no? So, if there are similar terms, in determining the LCD, it would not just multiplying the denominators, but we're going to need to simplify it. All right, so again, the problem looks like this. All right, so again, we are going to, first step is to verify. So for n is equal to 1, on the right, on the left side, that would be 1 over 1 times 2, and on the right, that would be n plus 1. So 1 over 1 half would be, sorry, 1 over 1 times 2 would be 1 half. This would be 1 over 1 plus 1, or 1 half is equivalent to 1 half. All right. So for n is equal to 2, again, what we're going to use are the first two terms. And then on the right side, that would be n over n plus 1. So on the right side, that would be 2, 2 plus 1. So it would be 2 over 3. All right. So again, just to recall the LCD, all right. If there are similar terms, you're going to use it once. What do I mean? If I'm going to do it here on the numbers, isn't it 6? If we're going to look for the prime factors of it, that would be 1 over 2 times 3. And you would observe that 2 is similar on both denominators, so that would be only used once. Now, the remaining term that has no similar denominator will just be multiplied. So, that would now become our LCD, wherein you're going to do this again. All right? So, this 2 times 3 is equivalent to 6, right? So, 6. 6 divided by 2 multiplied to 1 is 3. 6 divided by 6 times 1 is 1. Now, adding your numerator, it would become 4 over 6, or simplifying it, that would be 2/3. Again, which is equal. Now, for the last, for n is equal to 3, again, on the right side, that would be n plus 1. On the left, that would be 1, 1 times 2, 2 times 3, and 3 times 4. So on the right side, that would be 3 over 3 plus 1, or simply that would be 3 over 4. So we're going to determine the LCD again on the left side. So as I have said a while ago, if there are similar terms, you only use it once. So as you can see, on the first two fractions, 2 is similar. So does the similar terms be present on all the fractions? No. It is not necessary that 2 would also be present on the third fraction. But if there are similar denominators, you use it once. So 2 is similar, this one. Yeah, 2 is similar. 3 is also similar because 3 is present on the second and on the third. And then the last would be 4. So you do this process on all fractions. So 2 times 3 times 4. No? So the answer there would be 24. 24 divided by 2 times 1 is 12. 24 divided by 6 is 4 plus 1 is 4. And 24 divided by 12 is 2 times 1 is 2. So again, our denominator here is 24. So 12 plus 4 plus 2 is 18. So simplifying it, dividing both numerator and denominator by 6, that would be equivalent to 3/4. And as you can see, our mathematical statement is valid for step number 1. So we go to step number 2, which is the induction hypothesis. All we need to do there would be to substitute, right? To substitute your n to k. So that would be 1 over 3 times 4 plus 1 over k. K plus 1 is equivalent to k plus 1. So again, this is our equation 1. So for proof of induction, we are going to do the n plus k plus 1. Again, that k plus 1 term is the term we're going to add after the last term. All right? And if we're going to add a term on the left side, we should also add a term or whatever term we added on the left to the right. All right. Now, what would be our k plus 1 term? Our k plus 1 term would be coming from the star again, coming from this star. All right, so our term there is 1 over n plus 1. So we're going to substitute k plus 1, so that would be k plus 1, k plus 1 plus 1. Or simply that would be k plus 1, k plus 2. So the term that we're going to add on both sides would be 1 over k plus 1, k plus 2. Again, this is our equation 2. So in proving on our step number 3, we are going to prove that equation number 1 is equivalent to equation number 2. Again, this is where we added k plus 1 term, and this is where we substitute n to k plus 1. So for equation number 1, that is n plus 1. And then from equation number 2, that would be k plus 1 plus 1 over k plus 1, k plus 2. So on the left, we're going to substitute n is equal to k plus 1. So for all the n's, it would become k plus 1. So this would become k plus 1 plus 1, or simply k plus 1 plus 2. On the right side, again, if there are similar denominators, you're going to observe there are similar denominators. For your similar denominators or denominator, you only use it once. So k plus 1 is similar. So we're just going to use k plus 1 once. And then, since k plus 2 doesn't have any similar denominator, so we just multiply it to k plus 1. So again, that would be our LCD wherein you're going to do this process. So if we divide k plus 1, k plus 2 here, and multiply it to k, then it would be equivalent to k multiplied to k plus 2. You repeat the process on the second fraction, that would be plus 1. Now, we want to prove that it would be equivalent to this, right? That's what we want. But as you can see, if I'm going to simplify our fraction or the numerator of our fraction, this would become k squared plus 2k plus 1. Now, again, in mathematical induction, it is important that you still remember algebra because, as you can see, our numerator should be factored. Again, how are you going to factor, isn't it? If you're going to factor, there are two grouping symbols. If you remember the FOIL method, you can also use that. Alright? But normally for factoring, it is a trial and error method. So the factors of k squared plus 2k plus 1 would be k plus 1, k plus 1. Since k plus 1 is present on both numerator and denominator, we can already cancel it out. So that would be equivalent to k plus 1, k plus 2. And we already have proved that the right side is equivalent to the left. Then therefore again, we're going to just state the obvious, which is similar to what I've written on number 1 and number 3. So the mathematical statement is valid for n is equal to 1, n is equal to 2, n is equal to 3, n is equal to k, and n is equal to k plus 1.